In this video, we're going to look at how to find the general solution for a circular function. This is the kind of question where you aren't given a domain for your equation. For those who don't know me, my name is Chris Iannazzoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The general solution isn't that different to how you would regularly solve circular functions. We'll use the following process for solving the general solution. Let's look at a few examples. So, let's follow the process. If you've seen my earlier video on circular functions, then a lot of these steps are going to be quite familiar to you. If you need to revise this, then check the link above. The first 2 steps here aren't required, since this is a bit of a simpler example. So we're just going to move on to step 3, which is to figure out every solution within 1 revolution of the unit circle. Looking at our unit circle, that's going to give us solutions 4 pi over 3 and 5 pi over 3. Here's where things get a little bit different. What we do here is add 2 pi n to both solutions. That's it. This term is a stand-in for all the other possible revolutions that you could do around the unit circle. Recall that if you wanted to find additional revolutions, you would either add or subtract 2 pi to your previous solutions. That's what 2 pi n is telling us. N is an integer, which basically allows you to choose a value of n, and you would get that corresponding revolution as far as the unit circle solutions are concerned. If n is 0, then you're going to get the first revolution. If n is 1, you're going to get the second revolution, and if n was -1, then you would get the first negative solution. That pattern continues on and on. That's really all the general solution is. Alright, let's try again with cos. This time step 1 is relevant because we don't have our exact values expression. All we have to do here is divide by 2. This will get cos on one side and our exact value on the other. Step 2 isn't required here because we don't have a composite function, so we're just going to move on to step 3, which is going to give us the solutions 5 pi over 6 and 7 pi over 6. From here, we're just going to add 2 pi n to both of those solutions and we're done. This is a valid solution, but if you're looking to simplify it all the way down to the extreme, then here's what we can do. One thing about cos is that any given set of solutions will always be perfectly vertical to each other. This just means that it is an equal distance in the positive direction as it is in the negative direction. So one thing we can do here is just knock off one of those statements, usually the larger one, and then just put a plus minus in front of the smaller one. What that'll do is bring it down from having 2 separate solutions down to just 1 contained solution. This works because -5 pi over 6 is the exact same spot on the unit circle as 7 pi over 6. So we can take advantage of this by simplifying our expression. Tan has a similar thing going for it. Let's find out. Okay, well, in this case, steps 1 and 2 are irrelevant, so we can move on to step 3, which is going to give us the solutions pi over 3 and 4 pi over 3. From here, we just add 2 pi n to both of those solutions, and we could be done here if we wanted to. If you're looking to get the best possible answer, then once again, we can simplify this a little bit further. One quirk about the tan solutions is that they are always separated by pi. So, instead of finding 2 separate solutions and adding full revolutions to both of those, we can instead find 1 solution and just add half revolutions to just that one instead. This usually means that we drop off the larger solution, and then instead of writing 2 pi n for the first one, we're going to write pi n. You'll find that if you choose n to be 1, you do actually get that original solution that we knocked off earlier. If you are going to go this route of fully simplifying everything down, it does pay off to test some values of n to make sure it makes sense. We're going to finish this video off with one of the more complicated scenarios that you can come across. Now, it's very important that you do these steps in this order, otherwise you're going to get the question wrong. First, we're just going to get our exact values expression. This just means dividing both sides by 2. Now we move on to step 2, which is to simplify our expression by using a substitution since our function was a composite function. This is less important when it comes to general solutions, since there isn't a restriction on our domain, but it never hurts to simplify things. All we do is replace whatever's in the brackets with a single letter. I'll use u. From here, we're just looking for where sine is equal to -√3 over 2, and that's going to give us the solutions 4 pi over 3 and 5 pi over 3. Now here's the important bit. It's this stage where you add your 2 pi n. It's only after doing this where you rearrange to get everything back in terms of x, which just means dividing everything by 3. Don't forget, that 2 pi n term is part of your equation, so it also gets divided by 3. It's a very common mistake to put the 2 pi n at the very end and forget that it's also included in your rearranging. So this is my public service announcement to just say, don't do that, do this instead. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool. You should check it out. I'll see you there.